Okay, so today, guys, we're going to start on acceleration. First, a couple of reminders. Well, I guess just one reminder. Your graphing lab, your Need for Speed lab is due on May the 14th. Okay, that is this Thursday, so make sure that you've got it done. Okay, for that day. You can have me check it over today, or you can have me check it over on Wednesday. But remember, that I will be at the track meet on Tuesday, and so I won't be able to look over your stuff in scheduled help or at lunch on Tuesday. Okay, but I can look it over today or Wednesday, so take advantage of that. Other thing, obviously the final exam schedule has been out for a while, okay, but your final exam is June 19th, okay, at 9 a.m. That's a Friday. Okay, and I think it's only it's one of the first exams because our last day of class I think is the 16th or 17th. Okay, so it's pretty much right away after classes end. Right. Other reminder, obviously the long weekend is this coming weekend. Okay, and I say in all seriousness, the holiday is Monday, not Friday. Okay, it is not both. Okay, if you are not here on Friday, you will be expected to do everything we do, okay, on Friday if you're not here. Okay, no exceptions, no excuses. Okay, if you're taking Friday off, you're taking a holiday. Okay, not an excuse to not be here. Everybody clear on that one? Okay. All right, so a couple things we need to talk about for acceleration here. First off, we talked about that on velocity versus time graphs. Okay, and we said that when you're looking at a velocity versus time graph, if it shows this sort of a pattern, okay, where we have meters per second and seconds, okay, that we need to remember we can calculate acceleration from that graph. All right, we can calculate the slope of that line, okay, or if we had a velocity versus time graph that had several sections on it and they wanted the acceleration over the whole trip, we could still do that as well. Okay, we would just be using this formula right here. Okay, and really in either case we're using that formula. Okay, it's just that when we use it in this situation, we need to make sure that the points we use are actually on the line because we're calculating the slope of the line. When we have something like this where there's separate sections, then it's just a matter of taking final velocity, initial velocity, and we're finding the average over the whole trip, which is sort of represented by an imaginary line that's not on the graph. Okay, everybody follow me there? Right, so again, that's where that formula comes from. Okay, so we just need to remember that we can use that formula whenever. And today we're going to look at how we manipulate it to solve for other things. Okay, so far we've just used it to calculate acceleration. We're going to start running into problem solving where we're going to have to solve for VF, for VI, or for T. Okay, it's really not all that hard. It's not much different than V equals D over T was. Okay, so a couple of things here. First off, a word you've probably heard of, but a lot of people misapply it, and that is the word inertia. Okay, inertia is the tendency of an object to keep doing what it's doing. All right, right now, the inertia of this table is that it's going to stay there. I know that doesn't seem like rocket science, but that's Newton's first law. Okay, it's like the first law of physics. An object at rest will remain at rest unless acted upon by an unbalanced force. All right, everybody follow me on that? Are there forces acting on this table right now? There are, but they're not unbalanced. Okay, there are two forces right now acting on this table. One is obvious, and it's gravity. Gravity is pulling the table downwards. What's preventing the table from moving downwards? The floor. Okay, the floor is actually pushing back up on the table with a force equal to the force of gravity, and that's why the table doesn't go anywhere. Okay, there are no unbalanced forces acting on the table, so it stays put. Okay, the other part of Newton's first law that we call inertia, okay, is that an object traveling at a constant velocity will continue to do so unless acted upon by an external unbalanced force. Okay, now that is a little less obvious, okay, at least on Earth, right? Because if an object, if we're just coasting, we're usually doing what? Slowing down. Okay? Now that's because there are unbalanced forces in that situation. Right? Gravity's not unbalanced. Okay? It's balanced by the force of the ground. But What's the force that's actually slowing you down in that situation when you're just coasting, let's say on a bike or in a car? It's everywhere. It's almost always working against you. Friction. Okay? In a lot of cases, friction is air resistance, drag, okay, things like that. All right? So there is an unbalanced force in a situation like that. The only place where you would truly see Newton's first law for an object moving at a constant speed would be in space, where there's no air. And as a result, there's no friction. There's also no gravity if you're far enough away from the Earth, and as a result, there's really no forces out there. Okay? That means, should you become separated from your spacecraft and you're moving, you're pretty much screwed, because there's no way for you to stop, because you can't exert any forces to stop yourself in space. Right? I mean, even if you're, kind of like falling through the air, there's a real tendency for us to kind of try and swim a little bit. Okay? Does that create some resistance? It does. Okay? I mean, if you ever watched like those professional skydivers, if they want to fall fast, they tuck. Right? They do this and they get really small and they fall really fast. If they want to fall slower, they spread right out like this and they increase their drag and they slow their rate of which they fall slows down. All right? In space, you can flail around all you want. It ain't going to do you any good, okay? Because there's nothing out there to push on. So if you get moving, you're going to continue moving at a constant speed until some other force acts on you, and that could be a very long time. Yeah? So remember this if you ever become an astronaut. I told you this. Take a big wrench with you if you become an astronaut. All right? The reason you want to do that is because of one of Newton's other laws, which you won't learn about until Physics 20. Okay? Newton's third law. Every reaction has an equal and opposite reaction. You've probably heard that one as well before in your life, but it's always misapplied to some social situation. Okay? The reason you want to have the big wrench is if you can get your back turned to your ship and push and throw the wrench, you'll go the other way. Because when you push on the wrench, there's an equal and opposite reaction from the wrench to push on you. And so you'll accelerate a very small amount for a very short period of time, but it'll be enough to get you moving. And according to Newton's first law, once you get moving, you'll continue moving at that speed until acted upon by an external unbalanced force, hopefully crashing into your ship. Okay? And you'd be able to grab on then. All right? So that's kind of what inertia is. Okay? It's the tendency of an object to keep doing what it was already doing. So let's say you're in a nearly frictionless situation. You're on ice skates. Okay? So you're skating along and you're going in a straight line, you're coasting, and you want to turn. Okay? No, there's a number of hockey players in here. If you want to turn, what do you have to do? How do you turn on skates? I'm kind of doing it right now. Subconsciously, you think about it. Okay? Do you have to push to one side? Right? Usually you have to lean on the inside foot and you have to push a little bit with the outside foot, and that makes you turn a corner. Okay? Well, did you change your velocity? Yeah. But you exerted a force to do it. You exerted an unbalanced force in the other direction that pushed you this way. All right? So that's kind of what inertia is. Okay. So whenever the velocity of an object is changing, we say that object is accelerating. I think I said that part of your hypothesis for that Need for Speed lab had to be something about the definition for acceleration. That might be useful later. So anytime the velocity of an object is changing, the object is accelerating. Now, it is possible, okay, for an object's speed to not change, but for it to accelerate. How's that possible? Because notice, it says velocity here. It doesn't say speed. Okay, which one's vector, which one's scalar? Speed and velocity, which one's vector? Velocity. Okay, so the example I just used with the ice skater, okay, if you are turning a corner, your speed may not change. You might be going still at, let's say, 5 meters per second. But your direction changed. and that required a force, and that means you accelerated. A change in velocity can be as small as just changing which way you go. Right? It doesn't necessarily mean you have to go faster or slower, as long as you change something about your velocity, and that could include just your direction. Okay? We're not going to deal with that kind of acceleration in Science 10, but it's still important to note. Okay? All right, so the meaning of average acceleration is best illustrated, okay, by a plane during takeoff. And we might even want to use, instead of the word average acceleration, we might want to use the word uniform. And when I say uniform, I mean the amount that the velocity changes each second is exactly the same. All right? The reason a car is a bad example of uniform acceleration, or is not an example of uniform acceleration, is that cars have gears. And as a result, they accelerate differently in different gears. All right? If you're in first gear, you accelerate a lot more quickly than you do when you're in fifth gear. Right? If you've ever noticed that, right? If you're on the highway and you're trying to pass somebody and you floor it, you just don't get the same effect as if you're standing still and you floor it. Okay? Like it's a violent thing when you're standing still and you floor the car, and not that any of you would drive in such a reckless manner. Okay? But it's much more noticeable. Your acceleration is much greater in first gear than it is in fifth gear or sixth gear. Okay? Or if you have like a really new car, you might even have 9 gears. Okay? So your acceleration is different. It's not uniform. Whereas for a plane doesn't have gears. So its acceleration is quite uniform. And if you've ever been on a plane during takeoff, you know that you get pressed into your seat pretty much the same right at the beginning as you do at the end when you're finally leaving the ground. It doesn't really change throughout. All right. So what we've got here is this plane, okay, and at the beginning, where it's not moving, okay, we've got time 0, velocity is 0, okay, and after 1 second, okay, it's increased to 9 meters per second. But what do you notice about its position? Okay, the time intervals are the same. We're looking at this thing over the course of 3 seconds. What's happening to the distance it covers? It's getting bigger, all right? And we said that's why we get a curved shape on a position versus time graph. Okay, this would be inverted, obviously. This would be the x-axis here, but okay, we get a curved shape because the position changes more greatly the faster you go. All right. Okay, now remembering here a couple of other things. Anytime you see delta, that means change. And anytime you see delta or it means change, you're going to be subtracting final minus initial. All right, so whatever it is you're dealing with, whatever the delta is, it's final minus initial. Okay, and so we've got 2 deltas in this formula: the change in velocity divided by the change in time. Okay, and again, that's the slope of the line on our velocity versus time graphs. Okay. All right. Rather than use that example because it's in kilometers per hour, we'll move on to a different one here. Okay. We talked about these units the other day when we talked about velocity versus time graphs, so there's a little bit of review here. Okay. If I'm using the formula A equals VF minus VI over T, remember that my V's are in meters per second and my time is going to be in seconds, so my units will be meters per second or meters per second squared. All right, just telling us again how quickly every second, or how much faster are we going every second, right, is the units for that. Okay, we've kind of done that already. Okay, manipulation of this formula. 2.5 rules of algebra. Okay, if I want to move something, I do the opposite. What I do to one side, I do to, and what do I move first? Whatever's not attached to what I'm looking for. All right, so right now, this is set up for A. Okay, I want to solve for T. How should I change this formula? Jordan? Right, multiply both sides by T. All right, so T comes over here. And then what? And then divide by A. All right, so basically just like cross multiplication for that one. That one's pretty easy, right? It's the same as it was in V equals D over T. If I wanted to solve for the top, I just moved the bottom and switched the bottom over. Okay. Oh. All right, I want to solve for VF. So rules of algebra say move what's not attached first. What's not attached to VF right now? Well, A is already kind of where I want it. So I'm going to leave A where it is. Okay? I got to get VF by itself. So what else is not attached to VF? T. So let's move T. Let's get it over here. All right. Now what? I need VF by itself. So I obviously need to move VI. So what do? Add it. Yeah, exactly. What if I want to move something, I do the opposite. Right now I'm subtracting VI. So I'm going to add it to both sides. You're probably wondering what that little black mark was for. Okay, to make my plus sign with. All right. So I've got VI plus T times A equals VF. All right. Now, I want to show you why that makes sense from kind of a common sense perspective here. Right now, VF minus VI is the change in speed, right? Or change in velocity. It's delta V. And we're saying that T times A equals the change. So if I want to figure out what I end at, I should probably add the change to whatever I started with. Okay, and that's exactly what we're doing. When we move VI over to that side, we're adding it to the change. So we're taking what we started with, adding the change, and getting our final velocity. It's the same calculation you would do in your head, okay, if when you went to work in the morning you had $5, okay, and at the end of the day, okay, you wanted to know how much you were going to have if you were going to make $50 during the day. Well, you would take what you started with, 5, and add the change, 50, and you would get $55. Right? So that's what we're doing here. Everybody follow? Okay. So let's have a look at solving for something else here. Now I want to solve for VI. So let's think about the reasoning we just had. If I wanted to find VF, I took what I started with and added the change. So if I want to find out what I started with, I should take what I ended with and subtract the change. All right, that sort of makes sense, right? Okay, now mathematically, that's a little bit more moving around, but that's what we want to do from kind of a common sense perspective. Okay, so here's what I'm going to do. I'm going to move T over to here because it's not attached to VI, okay, and obey my rules of algebra. Okay, then, oddly enough, I'm going to add VI over to this side, just like I did before, right? But here's why I'm doing that. If I move VF, does this negative stay here? It does. I don't want to solve for negative VI, because what I find is when people do that, they forget that they've solved for negative VI, and then they have the wrong direction on it in their answer. Okay, this kind of eliminates the possibility of making that mistake. All right, so I'm adding VI to both sides, so I bring it over here just like I did before. Okay, and now you're saying, so what, Coder? You just showed me that. That doesn't solve for VI. All right, I want to get VI by itself now. What do I do with T times A? Right, subtract it to the other side. Okay, now how many of you are thinking, but Coder, they're multiplied, you can't subtract them? How many people are thinking that in their head? It's okay. Okay. Here's the thing. Think order of operations. Before I added VI to this, would I actually multiply those two numbers together? I would. Okay, because order of operations says you do multiplication and division before addition and subtraction, right? You do parentheses and then exponents and then multiplication, division. Okay, so really, T times A is just a number like X. So I could just subtract it over to this side because I will have already done that operation. All right, so that's what I'm going to do. I'm going to subtract, okay, T times A and that'll give me VI, which is exactly what we said, right? If we want to find what we start with, we should take what we ended with and subtract the change. Okay, and T times A is the change in speed, change in velocity. Okay, so it's going to take a little bit of getting used to, a little bit of practice, but it's not terribly difficult algebra. Okay, Good news is there's probably only one other formula you're going to use in this unit that would be about as tricky as that one in terms of manipulation. Okay? So again, like I said, you don't have to be good at math to do physics. I'm proof. Okay? I'm no good at math, okay? But I can do physics. Okay, so let's try a couple of examples here. So I want you to write this one down. Okay, I'll give you a couple minutes to write it down. Sprinter starts from rest and reaches a velocity of 16 meters per second in 4.5 seconds. What is his acceleration? Okay, so write that question down. I'll give you a couple minutes, and then we'll go over it. Okay, so in this question, guys, first off, there's some terminology that we need to be familiar with. What do you suppose it means if a person starts from rest? They're stopped, exactly. Okay, so if they come to rest, their final velocity will be 0. If they start from rest, their initial velocity is 0. But anytime you see the word rest, it means 0. Okay, they are not moving, they are at rest. Okay, so we want to write down our givens. We know that since this person starts from rest, VI is 0. Okay, and they reach a velocity of 16 meters per second. So that would be VF. And we know that that occurs over a time of 4.5 seconds. And they want us to find acceleration. Okay, so here's where writing down the givens starts to pay off for you. All I got to do is take out my formula sheet and find a formula that has those 4 things in it. That will be the formula I will most likely have to use. All right. Now, obviously, it's this formula because it's the only acceleration formula you have. Okay? That's the formula we're going to use. Do we have to manipulate that at all? Not for this question, because we're finding acceleration, right? It says, what is that person's acceleration? So we don't have to do any manipulating. We just have to plug in the numbers. So 16 minus 0 over 4.5. Okay, will give us our acceleration. All right, so we're looking at 3.6. What are my units? Meters per second squared. Okay. Is acceleration a vector quantity? It is. Okay, acceleration is a vector quantity. So I should probably indicate that since the speed or the velocity here got bigger, that this acceleration is positive. Okay, so acceleration is a vector quantity. Okay, questions on that one? All right, I want you to write down number 2 and give it a try. Okay, and then in a couple minutes, I'll go over how to solve it. So in this one, they're asking us, how long will it take? So what are we being asked to find, Shay? Time. Okay, and for it to accelerate from rest, so VI is 0 meters per second, okay, to 85 meters per second. At a rate of 22 meters per second squared. How do I know that that was the acceleration? Well, partly it was positive, but partly, look at the units, okay? Most common mistake people make is not the math here. Oftentimes people assume the acceleration is one of the 2 velocities. Okay, when really we should not make that mistake because we should look at the units. If it's in meters per second, it's one of the V's. If it's meters per second squared, it's A. All right, so always make sure you're looking at the units before you do a question. Okay, so I'm looking for T here. So A equals VF minus VI over T. Okay, we follow the rules of algebra. I want to solve for T, so I need to get it by itself. So the easiest way to do that is to move it over to this side by multiplying both sides by it. And then doing what with A? And then dividing both sides by A. All right, so there's our formula. Okay, now we plug in our numbers. So t equals 85 minus 0 over 22. All right, so we're looking at 3.86 seconds. Okay, being our time. So if you're looking at marks on a question like that, that would be 1 mark. Okay, choosing the correct formula is often a mark. Manipulation would be another mark. Sometimes I would give a mark for plugging in. So this would be a 4 or 5 mark question, okay, depending on whether I decided to give you a mark for plugging in the numbers correctly or not. Okay. Questions on that one? Okay. Try number 3 here. Write it down and give it a try. Okay, so let's have a look at this one here. So we're looking for final velocity. So we're looking for VF. That's the unknown. Okay, of a race car, if it starts at 15 meters per second. And that's positive, so it's forward. And it accelerates at positive 7.2 meters per second squared for 6.5 seconds. All right, so there's all our info. We're solving for VF here. Okay, so obviously we're using this formula, A equals VF minus VI, okay, over T. And we need to manipulate for VF, so I move what's not attached first, which is T. Okay, so T comes over here. Now I can move VI by adding it to both sides, so it's gone. And I've got this, VI plus T times A. All right, now I can plug in my numbers. So my initial velocity was 15 meters per second. Okay, the time was 6.5 seconds. And the acceleration was 7.2. Okay, so 15 plus 6.5 times 7.2, and your calculator should do proper order of operations if you were to type it in that way. Okay, so we've got a final velocity of 61.8 meters per second. And that should also have a plus sign on it, because the other two were also positive. What if it had accelerated at negative 7.2 meters per second squared? What would have happened then? Your answer would probably be negative, yeah. I mean, given how much the velocity changed by, it would probably be moving backwards after 6.5 seconds. Okay, and that's something that'll come up. I've often given questions kind of like in this sort of a context, a ball is rolled up a hill. Okay, well, if you roll a ball up a hill, originally the ball is moving up the hill. But after a few seconds, it's going to be moving back down the hill. All right, so the acceleration in that case is negative, but I might not outright say that. Okay, I might say a ball is rolled up a hill and its acceleration is this much. Okay, and I would expect that you would understand that everything accelerates downhill. Okay, if you initially roll it up, once it leaves your hand, it's rolling back to you, or it's accelerating back to you already. Okay, so little things like that, sometimes they come up. All right, and try number 4 here. Okay, so this one involves our trickiest manipulation of the formula. Okay, in this one we want to solve for VI. So how fast was the boat traveling initially? Okay, so VI is the question mark. It accelerated to 30 meters per second. So that's VF. Okay, at a rate of 2.6 meters per second squared. Okay, and that would be positive. This is positive. And it did that over 8.9 seconds. So A equals VF minus VI over T, and we're trying to solve for VI. So we're going to first multiply both sides by T, then we're going to add VI to both sides, okay, and then we're going to subtract t times a back over to the other side so that we're taking the final velocity and subtracting the change, leaving us with the initial velocity. All right, so now we can plug in our numbers here. So we've got positive 30 meters per second minus 2.6 times 8.9. Okay, so 30 minus 2.6 times 8.9. Whoa, no, 89. Okay, so we're looking at 6.86, so 6.9 we'll say, meters per second. And that would also need a positive on it. Okay, are these starting to make sense? Okay, same as always, you've just had one example of every manipulation of that formula, okay, just like I always do for you, so probably not a bad idea to review this podcast at some point, okay, if you're studying for your acceleration stuff. All right, here's that one I was telling you about. I want you to try it now. Ball rolled up a hill. Okay, so give this one a try. Okay, so let's have a look at this one here. So we got a ball rolled up a hill at 4.5 meters per second. So should I make up the hill positive or negative? Positive, okay? I mean, it doesn't matter what, as long as you make down the hill the other, okay? But they got to be opposite. All right, so I'm going to make up the hill positive at 4.5 meters per second. Okay, it accelerates down the hill at 2.1 meters per second squared. Okay, so I've made that negative because it's in opposite direction. Okay, what's the velocity after 3.5 seconds? Okay, so we're looking for VF. So it's not a hard manipulation. A equals VF minus VI. That's a terrible V. VI over T. Okay, so we multiply both sides by T. We add VI to both sides. Okay, and we've got VF. All right, so here's what we got to do then. We've got positive 4.5 plus negative 2.1 times 3.5. All right, so 4.5 plus negative 2.1 times 3.5. Whoops, I got an extra times in there. Seemed like that wasn't quite right. That should be plus, not times. All right, negative 2.85 meters per second. Now, when I put my final answer on here, though, should I leave it as a negative? Or should I maybe write somewhere else something different? Did the question give me positive and negative? What did the question give me for directions? Up the hill and down the hill. My answer needs to reflect what the question gave me. Yes, I turned those directions into positives and negatives. But when I go back to my final answer, it needs to reflect the directions originally given in the question. So my final answer should be that VF equals 2.85 meters per second downhill. Okay, and we don't want to say down, because down is different than downhill. Down is vertically down. Okay, downhill is some angle that's not 90, okay, degrees, right, to the vertical, or to the horizontal, sorry. Okay, questions on that one? All right, so that's something to keep in mind about vectors. Yes, you can use positives and negatives when the question gives you that, but the question gives you north and south, or right and left. Make sure your answers reflect the question's vectors that were originally given. If you were using triangles for v equals d over t and somehow hiding it from me, you're now dead. Okay? Because you can't use a triangle now. Okay? Triangles won't work anymore because they don't include that plus and minus part. So if you were still using triangles, you need to come and see me and learn how to do algebra. Okay? I will not allow you to use a crutch. Okay, you must learn to walk on your own. Okay, so make sure you're not using triangles anymore because they will not work anymore. Okay, try this one. Write it down and try it. We got lots of examples today. All right, let's have a look at this one here. So it's thrown upwards in the air at an unknown velocity. That means we don't know how fast it's going at the beginning of the question. So VI is unknown. All right. We know that it's in the air for 6.5 seconds, so we know the time. We also know that anything in the air, on Earth anyway, accelerates at negative 9.81 meters per second squared, or 9.81 meters per second squared, downwards. Okay. Here's the trick with this one, because it is really, sorry, the final velocity is, is 2.4. Sorry, I was thinking it was a really tricky one. Okay, so 2.4 meters per second, and that is negative because it is downwards. All right, now I can solve for VI. All right, so A equals VF minus VI over T, so we multiply both sides by T, we add VI to both sides, okay, and then we subtract T times A over to this side. All right, so we have that VI equals VF minus T times A. All right, VF was negative 2.4 meters per second, and we're subtracting the 6.5 seconds multiplied by negative 9.81. Now, what's going to happen there? I'm going to get a negative number when I multiply 6.5 by negative 9.81. When I subtract a negative, I'm really doing what? Adding. So is this going to give me a positive number? It is, and that's good because I'm pretty sure the question said I threw it upwards. Okay, so if you were to do this question and got a negative number and the question specifically said you threw it upwards, you know you did something wrong mathematically somewhere along the way. So a good reminder to always check to make sure your answer fits with the context of the question. Okay, like for example, if it's, you're doing a question about a turtle, all right, and you get that they're moving at 2 kilometers per second, you probably did something wrong somewhere along the way, unless this turtle was fired from a very big cannon. Okay, right? So the little things like that. Always make sure your answer makes sense. All right, so we plug in our numbers, okay, and we'll start out with negative 2.4, okay, minus 6.5 times negative 9.81. Okay, so it was thrown upwards at 61.4 meters per second. I don't know who threw that, because that's faster than any major league pitcher could possibly hope to throw anything. Okay, because that's about 230 kilometers an hour. Okay, yeah, generally you don't see too many guys throwing that fast. Okay. Okay, and I would put that direction on there as well. My initial velocity is up. Okay, it was thrown vertically upwards, so I need to reflect that in my answer. Questions on that one? Okay, that's really, guys, that's really about as tricky as it gets. The ball rolling up the hill, or these ones here where you got 2 different directions, are about the only trick I can throw at you. All right, and really all you have to remember is that you have to assign positive to one direction and negative to the other. Okay. All right, now I'm going to give you a worksheet here. You won't get much time to work on it today, but that was my plan, because tomorrow that's what you're going to be working on when I'm at the track meet. Okay, so you'll be working on this worksheet, okay, getting it done. You will not have a quiz tomorrow, because obviously I'm not here, okay, but you will have one on Thursday, and it is going to be on using this acceleration formula. So you best get that sheet done tomorrow so you know what kind of questions you need to ask. There will be a podcast that will be played, but kind of just infrequently throughout, because it'll be the answers or the solutions to questions that are on this sheet that people generally have trouble with. Okay? Everybody with me there? All right. Okay, now there is one thing that gives people trouble on the very first question, so we do need to go over that, okay, right off the bat here. We've got things that are in seconds, things that are in meters per second, and then we've got something in kilometers per hour. Right? Do our units match? Do they need to? Yes, okay, so we've got to change the kilometers per hour into meters per second. Okay, now there's a little trick to that. It's what we call a compound conversion, but you'll have this shortcut because you'll remember it after this. Okay, if I want to convert 140 kilometers over hours, because that's what kilometers per hour is, into meters per second, I've got to convert both the kilometers to meters and the hours to seconds. All right, so essentially we do two multiplications here. All right, first off, if I want to convert kilometers to meters, okay, I set up the conversion for that. How many meters in a kilometer? 1,000. Okay, so I need to multiply by 1,000. Okay, so there's 1,000 meters in 1 kilometer. So I just set up that conversion. Kilometers on the top, kilometers on the bottom, and it'll cancel. And I'll now have meters per hour, which doesn't do me any good. I need meters per second. All right, so I need to set this up. In 1 hour, there are how many seconds? Everyone wants to say that. It's so ingrained in us, isn't it? It's 3,600, okay? 3,600 seconds. All right, and again, I've got hours on the top and hours on the bottom. So my hours are going to cancel, my kilometers are going to cancel, and I'm going to be left with 140,000 over 3,600, okay? Rather than look at that, I'm going to put these two fractions together right here. So I'm going to have 140 multiplied, okay, so 140 over 1, multiplied by 1,000 over 3,600. So if I did this in order, I would go 140 times 1,000 and then divide by 3,600. Could I just skip this and take out that? Like, could I divide both of those by 1,000 and get rid of that 1,000? So I'm left with 3.6 on the bottom and 1 on the top. So in the end, this is what I'm left with. What I had in kilometers per hour over 3.6 will give me meters per second. Okay? So if you want to convert kilometers per hour to meters per second, divide by 3.6. If you want to go the other way, multiply by 3.6. You might want to write that on your formula sheet. That might be something useful. I'm not going to make you do that on a test, okay? But just so you remember, because it does come up occasionally where you got to convert kilometers per hour to meters per second. That's how you do it, okay? So that's the answer to part A. That will get you your 38.9 meters per second.